Viewers, in today's lecture, we will derive a relation for electric potential due to a point charge. We find the direction of electric potential due to a point charge. Viewers, in today's lecture, we will find the relation. We will derive a relation for an electric potential due to a point charge. So let us consider the positive charge, and the direction of electric field lines always radially outward from a positive charge. If we follow the electric field line due to positive charge, let's here we take a point A, and the distance from the charge at point A is represented by RA, and we take another point B. The distance from charge to point B is represented by RB. The distance between A and B will be represented by delta R, and the midpoint of A and B let is R. So now delta R, the distance between A and B, change in R. If we move a point charge from B to A, if we are moving a point charge from B to A, so if we are moving a charge from B to A, then delta R will be equal to x2 minus x1. Higher distance, final distance A, RA minus lower distance or initial distance RB. This will be taken only if we move charge from B to A in this direction. Then B will be initial point and A will be final point. So distance is always equal to final minus initial point. So this will be only in case when charge charge Q is moving from point B to point A. Then B will be taken as initial point and A will be taken as final point. So then change in distance or distance between 2 points will be equal to final minus initial, RA minus RB. So if now we assume that if point A and point B are lying very close to each other, let point B is here, that point B is here. So if point B and point A are lying very close to each other, then the distance between A and B nearly equal. So then we assume that RA, distance of point A from charge RA, is approximate equal to distance of point B from the charge, positive charge. So in this case, let V represents both the distances with R, because both the distances are same, equal. So RA, we represent RA with R and RB with R. So in that case, the RA multiply by RB, RA is equal to R and RB is also equal to R. So R into R is equal to R square, RA into RB is equal to R square. So this is our equation A, this is our equation B. And now we will find using the potential gradient, as we know that change in potential is equal to minus E into D. Here D is replaced by del R because distance between 2 points is del R. So here D is replaced by del R. So change in potential. change in potential del V is equal to electric field intensity. Electric field intensity always equal to kq over r square, kq over r square, and del r is equal to ra minus rb. So if we multiply minus sign, so we left with kq r square. So minus will be plus rb, and plus minus will become ra, and r square will be replaced by r square. R square will be replaced by ra into rb. So ra and rb will be divided with this and this. So kq rb, ra into rb minus ra divided by ra into rb. So ra will cancel out with ra, rb will be cancelled out with rb. So we left with change in potential is equal to kq. K is Coulomb constant and its value is 1 over 4 pi epsilon naught. So it will be 1 over ra minus 1 over rb. Here change in potential. If we are moving from charge, so if we are moving away from point charge, then the potential at A is higher and potential at B will be lower, because we also discussed that the potential due to if we are moving away from the charge, then the potential difference always decreases. Electric field intensity always decreases. So if electric field intensity decreases, then E is equal to minus del V over del R. So if E is decreases, then the electric potential must also be decreases, and formula for electric field intensity is kq over r square. So r square is inversely proportional to electric field intensity. If when we move away from the charge, then the electric field intensity will be always decreases. So if electric field intensity decreases, then electric potential must always be decreases. So if we are moving away from the charge, so then the potential at A will be higher and at potential at B will be lower, because B is the distance of B is greater than the distance of A from the charge. So change in potential will be equal to higher potential. Potential will be higher at point A and potential will be lower at point B. So higher potential minus lower potential K over 4 pi epsilon naught 1 over R A minus 1 over R B. Now we suppose that point B is point B lies at infinity. Point B lies at infinity because we are calculating to electric potential due to a point charge, due to at a single point. So here we calculate the potential at 2 points, point A and point B. Now we are going to calculate the potential at a single point. So for this we must take point B at infinity. If point B lies at infinity, then we will be able to find the electric potential at point A. If we take point A at infinity, so if point A is at infinity, then point B must be at infinity, because point B is further away from point A. So therefore we take point B at infinity. So we suppose that if point B approaches to infinity, then potential at B must be equal to 0, because at infinity the electric field of that charge must be equal to 0. So if electric field of that charge is equal to 0, then electric potential must be always equal to 0. If E is 0 at infinity, then the potential difference must also be 0. And then if point B lies at infinity, then 1 over RB is equal to 1 over infinity. So something divided by infinity equal to 0. So 1 over RB must be also 0. So we put here VA minus potential at B is 0 because we consider the point B at infinity, and Q over 4 pi epsilon naught 1 over RA minus 1 over RB also equal to 0, 1 over RB also equal to 0. So we left with potential at point A is equal to Q over 4 pi epsilon naught into 1 over RA. So this is the electric potential due to charge Q at point A. So we found a potential at point A which will equal to Q over 4 pi epsilon naught into 1 over RA. Generally we can write it generally because generally we always take any point R. So for any point R, potential at any point R must be equal to K Q over R. So this is the electric potential because 1 over 4 pi epsilon naught is equal to K. So electric potential at any point is always equal to KQ over R. R is a point at which we can find the electric potential. So if we can see here, the electric field intensity and electric potential both are inversely proportional to distance from the charge. If we are moving away from the charge, then the electric potential and electric field intensity must always be decreases because they are inversely proportional to distance from the charge. If we move away from charge, then the value of electric field intensity and electric potential continuously decreases. So this is our required result, and now please don't forget to subscribe our YouTube channel and like our videos for watching more interesting and informative physics lectures. Thank you.